Welcome, ladies and gentlemen. This is our third video in the equilibrium unit. This is going to be on the third primary topic of equilibrium, calculating concentration of a species when you have been given a K value. So in this video, you're going to see us working with ice charts again. Ice charts are a critical component of this, and I'm going to go through a practice example and then talk about how this type of problem is slightly different, and it really is only slightly different when you're dealing with Ka, Kb, or Ksp problems. So again, this is our third primary topic of equilibrium. These are the big three that we have to be able to do no matter what, calculating concentration from K. So it's a little bit of the flip of the previous one. We were calculating K when we were giving concentration. So just like in the last video, there are three fundamental steps to all equilibrium problems. First of all, you need to write a reaction if a reaction has not been provided to you. The reaction that you're going to write will depend on the information you've been given. If you've been given a Ka value, you're going to write a Ka reaction, an acid dissociation reaction. If you've been given a Kb value, then you write a base dissociation reaction. If you've been given a Ksp value, then you want to write a solid dissociating into its ions, a solubility product dissociation. So first step, write a reaction. Second step, fill in an ice chart. This is exactly the same as from the last video. You fill in an ice chart as best you can for that reaction, as fully as possible. Maybe you don't fill it out with numbers, but you fill it out. Then once you've filled out the ice chart, then you go to the equilibrium expression, products over reactants raised to their coefficients. You plug in the values that you got from your ice chart and you solve. You solve for something, and if it's not what the problem is asking for directly, then you have to do maybe just a tiny bit of modification to get it to what the problem is asking for. So in calculating concentration, when you've been given the K value, what will be different about this process is that you will have unknowns in your equilibrium expression, meaning we can't fill in our ice chart with numbers. We will have unknowns. We will have X values in our equilibrium expression because we don't have enough information to completely fill it out. But you do know the value for K. So the idea is we'll have the unknowns in the expression in the products of our reactants raised to their coefficients, but we're setting it equal to a value that we do actually know. And we can use this to solve for pH if we have an acid-base problem, because if you think about our acid dissociation reaction, we have HA goes to H plus plus A minus. Well, that's going to mean that in our equilibrium expression, we have H plus as an X value. So if you manage to solve for X, then that's either going to be H plus or OH minus, depending on whether it's acid or base. And so you can simply take the negative log of that value once you have it to get pH. And that's a very, very common type of equilibrium problem. So an example problem, how do you calculate concentration when you've been given K? So given 0.1 molar COCl2, determine the equilibrium concentrations of carbon monoxide and chlorine, given that the Kc value for this reaction is 2.19 times 10 to the minus 10th. So a reaction has been supplied here, so we can sort of skip that first step of writing the reaction, but we do want to go on to the second step of our process, which is fill in an ice chart. So I have my ICE, and I'm going to just read the problem. What information has been given to me? Well, it says that we have 0.01 molar COCl2, and unless stated otherwise, if it's a reactant, that's going to be your initial concentration, meaning that they're saying that we're starting with this certain amount of reactant. And I'm reading the rest of the problem, and I realize that is the only molarity that has actually been supplied here. So I don't have any other concentration values given explicitly, but I do have two more concentration values that are given implicitly, and that's the 0 molar for the products, right? Products, you don't start with any unless the problem specifically tells you otherwise, and it will be very explicit about saying, hey, and we are starting their reaction with a certain amount of product. This problem doesn't say that, so I know that it's starting at 0. Now, I have to fill out an ice chart, so I need to fill out the rest of this, but I don't have any more numbers, which means I'm not going to use any more numbers to fill out this ice chart. Now I'm going to use unknowns. I have no other concentration values, but I do have a value of K. I still need to fill this out. So I'm going to think about the change for each of these things. Well, these guys are in a 1-to-1 1-to-1 relationship, which means that they're all going to change by the same value. So I'm going to plug in X. I don't know what X is because I don't have any more concentration information, but I do know that because of their ratios, they will change the same amount. But now I need to think, how are they going to change? Are they going to go up or are they going to go down? And that's based on whether or not they're reactants or products. Reactants decrease, so the COCl2 is minus X. Products increase, they're being produced, they're being made. So the CO and the Cl2 are both plus X. And now that I've done that, I can fill in the equilibrium row. So I know that the equilibrium concentration of COCl2 is 0.1 minus X, and the CO is X, and the chlorine is X, because of that one-to-one-to-one relationship. And that's what I mean when you say you fill in an ice chart as best you can. This is the best that we can fill this out. We don't know what the change is exactly, but we do know that it will be the same for each. So once I've done that, now you want to go to your expression. Filling in the ice chart is the second step of our equilibrium problem-solving process. Going to the expression and plugging in is the third step. So the expression for this reaction, products over reactants raised to their coefficients, so CO over Cl2, CO times Cl2 over COCl2 is equal to 2.19 times 10 to the minus 10th. We know that because it says so here. So we have a value that we're setting that equal to. Now we're just going to plug in, right? Because we have values. I'm going to plug in from my equilibrium row, and I'm going to get x squared over 0.1 minus X is equal to that 2.19 times 10 to the minus 10th. Well, there's only one unknown in this. You can solve for X. I know you can. Math has been training you to do that. Here's the thing, though. Here's the thing. If you want to solve for X from that previous thing, you're going to have to use the quadratic equation. You have to, right? If you go back and look at this, we have X squared over 0.1 minus X equals 2.19 times 10 to the minus 10th. That's going to wind up being a quadratic. You're going to get two answers, and you have to evaluate both of them. Chemists are lazy. Yes, we are. And we want to make our lives easier. So we actually have a strategy to make this type of problem significantly easier. And it's an assumption. My notes from when I took introductory chemistry my first year of college, my college professor spoke about this, and he actually called it the golden approximation. And this is our assumption. If K is significantly less than 1, and what we consider to be significantly less than 1 is on the order of 10 to the minus 4th or smaller. So if K is very, very small, then we can assume that X is negligible in comparison with the concentration that we're subtracting it from. So this assumption right here, 0.1 minus X is approximately 0.1. Now the reason that we're making this assumption, the reason that this assumption is quite often valid, if K is significantly less than 1, that means that you really don't have a lot of products at all, correct? It means that you have a lot of reactants, right? If products over reactants, K is very small, you have a lot of reactants and not so many products. So X is very, very small. And we're saying that X is so small that when we subtract it away from 0.1, we still essentially get 0.1 because X is so tiny, it's not really having an impact on the 0.1 value. This is like the same idea if you compare Bill Gates' salary to Mrs. Julian's salary. So let's say we have Bill Gates' salary and then we subtract away from it Mrs. Julian's salary. He's not going to notice. He will not notice the difference because Mrs. Julian's salary is so small in comparison to Bill Gates' salary that, okay, you take away Mrs. Julian's money and you still basically have all of Bill Gates' money. He won't notice. So you assume that if you take away Mrs. Julian's salary from Bill Gates' salary, you still basically have Bill Gates' salary. That is the idea, that X is so small in comparison to that initial concentration. You subtract it away, you will not notice the difference. Now, this makes our math way easier, and it also allows us to do this problem on multiple choice questions where we do not have a calculator and cannot use one to solve the quadratic equation. But it comes with a couple stipulations. If you're doing this on a free response question, first of all, you have to indicate that you are making the assumption. So you have to show me this right here. Indicate that you're making this assumption. And by the way, this right here is how you indicate. You just say 0.1 minus X squiggle squiggle 0.1. That's enough to indicate that you're making the assumption. Then you have to go back and check for percent ionization. If percent ionization is less than 5%, then we consider the assumption to be valid. So basically the two rules about this assumption are, number one, please indicate that you're making it, and number two, go back and check and make sure that the ionization was in fact less than 5%. If it's less than 5%, then it's okay to assume, then we're basically saying that X is super small, and it's okay to use this assumption. If percent ionization is actually greater than 5%, you have to use the quadratic equation in order to solve for it. Now, listen up. If you do not want to make this assumption, if you think that this sounds dumb, and you want to use the quadratic equation, then I have an additional set of rules for you. Number one, you must show me the complete quadratic equation. Number two, you must show me the two possible answers you get. Number three, you must explain which of the two possible answers is correct. You have to use words and use sentences in order to do that. So in either case, you have to do something. So it's not like you have to do more work for the assumption. No, you have to, if you want to use a quadratic, show me the complete quadratic, show me the two answers, and explain how you know which one is correct. Or you can simply use the assumption, show me that you're making the assumption, and then go back and check it when you're done. I strongly encourage you to do that. So if we go back to our previous problem, then we're going to use our assumption. So I'm going to say 0.1 minus x is approximately 0.1. This then changes the quadratic, right? So instead of having x squared over 0.1 minus x, now we have x squared over 0.1 is equal to 2.19 times 10 to the minus 10th, and suddenly it's way easier to solve, and I mean way easier to do. And this, by the way, is a sort of math you would be expected to do on a multiple choice question without a calculator. So solving this, I get x is equal to 4.68 times 10 to the minus 6 molar. Now looking back at our ice chart, and you do need to look back at that, x in the ice chart represented the concentrations of CO and the concentrations of Cl2, and that's what the problem was asking for. So by solving for x, we have in fact answered the problem. But remember, you need to check your assumption. The way you check your assumption to see if it's less than 5% ionized is simply do your x value, which is basically the percent essentially that's associated, the products, the percent products essentially. So you're going to do your x value, 4.68 times 10 to the minus 6, and then you're going to compare it to the thing that you subtracted it from, 0.1. You want to make sure that basically x is less than 5% of the thing that you compared it to. So I'm checking to see that x is in fact less than 5% of 0.1. So I'm multiplying this by 100 because it is percent. And when I do this, I get a very small number. I get something that's 0.005%, which is definitely less than the 5% that we're looking for. So you know what, this assumption is totally valid, and I'm good to stick with my answer. And that's how we do calculating concentration values when we're given a K value. We use X in our ice chart, and we will be making an assumption if K is very, very small. So what's different about doing this in a KA problem? Well, this is an example question right here of a KA problem where they're asking for concentration from a value for K. What is the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius? And then they give you the Ka value for acetic acid, which, by the way, Mrs. Julian has memorized because that's how often the Ka value for acetic acid actually comes up. So right here, what is the pH? Notice that's basically concentration, because we calculate pH from taking the negative log of the hydrogen ion concentration. So this is a calculating concentration from K. It does usually ask for pH. So when you're solving this, and this is an acid dissociation problem, X, when you make that, when you're saying the unknown, X will be equal to the equilibrium concentration of H+. So if you solve for X, you just need to take the negative log of your X value, and then you're going to have pH. Now, notice this problem up here does not give you a reaction, but it's a Ka problem, so you want to write the acid dissociation reaction. They gave you Ka, write the equation that goes along with that Ka value. That's how you know the reaction you're going to write. What K value did they give you? Write the reaction that coincides with that. Remember, always show that you're making the assumption. So in this problem, it's 0.3 molar. So in this problem, it would be 0.3 minus x. So you'd want to assume that that's approximately 0.3. And then check at the end when you're done. And that's it. I mean, literally, that's all that's different about it. It's not really all that different. KB problem. What's different about KB? Again, read the problem. Determine the pH of a 0.25 molar solution of ammonia, and then they give you a KB value. And I always find it interesting that the KB for ammonia is actually the same value as the Ka for acetic acid, because I'm a nerd that way. Now, again, we're asking for pH, but this is a base dissociation problem. So the reaction that you're writing, right, NH3 plus H2O yields NH4 plus OH minus, because this is base dissociation. Now, X is hydroxide. So, you know, it's like one additional step when you want to get pH. So, okay, you get X is hydroxide, you take the negative log of it, you get POH. Make sure you go back and think, okay, I'm going to do 14 minus my POH to get pH. Again, they give you KB, so you write base dissociation reaction. Sometimes, and I've definitely seen this done enough times to tell you about this, sometimes they won't give you KB value directly. Sometimes you're going to need to do the manipulation. Ka times Kb for a conjugate acid-base pair is equal to Kw. Sometimes, like, maybe they would give you the Ka value for NH4 plus, but they give you NH3 in the problem, and so you're not actually starting with any ammonium. You're only starting with ammonia. So sort of bear that in mind. Sometimes you need to do some manipulations to get the correct K value that you need. And remember, as always, show the assumption that you're making, check it at the end. What's different about a KSP problem? Well, if we have an example right here, calculate the molar solubility of cadmium-2 hydroxide, and they give you the KSP value right there. Notice they don't give you any concentrations because the reactants in a KSP problem are solids, so we don't really talk about the molarity of solids explicitly in the problem, but the only thing that are going into the expression are products, so you're basically going right to, you know, what would be the change for the products, and you just have X's and nothing on the denominator. You're writing the KSP reaction, right? They give you a KSP value, so you have a KSP dissociation reaction. They ask for molar solubility. Remember, molar solubility is really just another way for talking about what is the molarity of the dissolved ions in cadmium-2 hydroxide. Now, your unknowns, when you solve this, because you're going to use the exact same process, you're going to write a reaction, you're going to fill in an ice chart, you're going to plug into the expression. Your unknowns, X in this case, would be related to the ions, cadmium and hydroxide. Watch your ratios, because in this case, right, cadmium hydroxide are in a 1:2 ratio. So just to show you an example, we'd have the cadmium hydroxide goes to CD2 plus 2OH minus. I don't fill out the column for the cadmium hydroxide because it's a solid. I know that I'm starting at 0 molar for these guys, but because the cadmium is in a 1:2 relationship with hydroxide, it's going to be plus X for the CD and plus 2X for the OH. So that's what I mean when I say watch your ratios. Now, if we want to get the molar solubility of cadmium hydroxide from a problem like this, you solve for the value of X. Now, X, in this case, X is going to be the concentration of the cadmium. But then you use mole ratios, to say, well, if the cadmium ion is, I don't know I didn't solve this problem, but let's say it's, I don't know, 1 times 10 to the minus 4th or something like that. If the cadmium ion is 1 times 10 to the minus 4th molar, and it's in a 1:1 ratio with the cadmium hydroxide, which is the problem, which is what the problem is asking about, then I can say, okay, well, if the cadmium is this, then so must the cadmium hydroxide. It must be the same value because they're in a 1:2 ratio. So you turn the molarity of the ion into the molarity of the solid using mole ratios, and that's what's a little bit different about this type of problem. Careful, careful, careful. Sometimes they ask for the solubility in grams per liter, in which case you do the same procedure. You get sort of the molarity of the thing that it's asking about through the equilibrium problem, and then just use gram formula mass at the very, very end. If they ask to compare solubilities of two different solids, which they have done more times than I can count, then actually calculate the molarities of the species. Actually do what it asks for, because solubility is basically asking about molarity. How many moles per liter will be soluble? And compare those numbers. Do not just compare KSP values. KSP is not solubility. Molarity is solubility. KSP is about the ratio of dissociated ions to solid. If they're asking to compare solubilities, actually calculate molarities of ions and compare those. Careful working with ratios. You're likely to have x and 2x like we did in this problem up here. Oh my God, more times than I can possibly tell you, AP Chem students, because you're very smart about some things and you're very dumb about others. Offense intended. You will make the stupidest mistakes on these types of problems. I have seen this way more times than I want to even think about. And this, by the way, is coming from the equilibrium expression up here, right? Because the equilibrium expression for this, KSP is equal to cadmium times the hydroxide squared. So you're plugging in, you're like, okay, so KSP is going to be equal to x times 2x squared. You're plugging it in, right? Oh my God, you guys, x times the quantity 2x, which is squared, is not 2x cubed. Do math like you know how math works. You have been through so many math classes in your life. Do not make that stupid mistake. Square the entire quantity of 2x, which is 4x squared, and then you multiply it by another x and you get 4x cubed. Do that. Do that. Please do that, because you do not want to make a dumb arithmetic mistake derail your entire equilibrium problem. So you're like, hey, I'm really good at this. I can do equilibrium problems and I feel really confident. You're doing all this sophisticated chemistry, and then you make a dumb math error. You do not want the dumb math error to bring you down. The equilibrium is complicated enough. Get your arithmetic right. So be careful of that in KSP problems. I've seen this far too often. Far too often. Don't do it. So tomorrow, when you do this problem set, you're basically going to be seeing all the different types of problems. You're going to see a normal like KC problem, and then you're going to see KA, KB, and KSP. Get practice with all types.